Good afternoon. Welcome to the latest in our 1 p.m. presentations from SMPTE Philadelphia. I thank you all for attending and thank you for joining us in all of these as a venture down this new path of webinars as opposed to in-place meetings. Today, we're doing a presentation from Canon on 3 formats, a transition from HD to 4K and beyond, looking into the current state-of-the-art imaging resolution, zoom lenses, focal ranges, HDR, and a couple other things, creative aspects of image format size in terms of image ranging, depth of field, and diffraction. Larry Thorpe from Canon is going to look at these image formats. He's going to look at 2/3 inch formats, 4K, UHD, and a bunch of other fun topics for us. And along with this, we'll have a Q&A. Now, with the Q&A, it's about a 15 to 20 second delay before we see it. For the most part, we will try to answer in text form some of the minor questions, but other ones will wait till the end of the presentation from Larry to answer most of the questions. At this point, I'm going to turn it over to Dover, who's a past chair of SMPTE Philadelphia, to discuss and Canon a little bit before we begin the presentation.
Hey guys, so a little bit of background on Mr. Thorpe. He joined Sony Electronics in 1982, where he spent more than 20 years in HD TV development. Prior to Sony, he worked for RCA's broadcast division from 1966 to 1982, where he developed a range of color television cameras and telecine products. From 61 to 66, he worked in the designs department of the BBC in London, England, where he participated in the development of a range of color television studio products. He is an IAT graduate, and he received his Chartered Engineer and MIET distinction in 1965 from the Institution of Electrical Engineers in London, England. He started working at Canon in 2004 and is still there now, where he is known as the godfather of HD TV. So, the very eloquent Mr. Thorpe, take it away, sir.
All right, let's see if I can share my screen. And I just need to find the right one. It's eluding me again. Hang on, there we go. There it is there, I do believe. Is that it? Yes, it is. Can you see that?
Yes, sir.
Good. Let me just get rid of this, and then I will open that up to full screen. Full screen. Come on there. Where am I? There we go. All right. So I will put the first slide up, and these are the 3 formats that I'll talk about. That little one in the bottom is still the center of the universe for global television, broadcast television. The 2 at the top are the hot topics in the world of digital cinematography. And of course, cinematography today does range very much into television production, as we'll mention. Going to the little one first, the 2/3 inch format. It's hard to believe that it's almost 45 years in our industry, and it has marched through the analog, the digital, and into the HD TV, and now into 4K UHD TV. What really has extended its life was that 1992 standardization project that standardized the mount between the lens and the camera for the first time in the broadcast industry. They felt they simply had to do that in a timely fashion for HD TV. And these were the companies that were involved in that standardization, which was driven by NHK. In their wisdom, they did see that this was essential for the future of high definition television. And that standard specifies the mechanical, optical, and electronic aspects of the B4 mount, as it's affectionately known. Now, when we come to lens specifications, they separate into operational specifications, which are important to those who use the lens, and the production folks. And there's the technical specifications of interest to engineers, and anyone who's interested in making the purchasing decisions will look at these specs. The operational specs, I list here, the primary ones. This is what you'll find rich in all of our brochures from all of the manufacturers. We give you lots of numbers and information on these specs because they are important to the usage of the lens. What we don't give you an awful lot of information on is the optical image performance specs. And I list the prominent ones here. Each one is an interesting topic of discussion. And each one is generally surrounded by gobs of data. And the reason there's so much data associated with them is that they're dynamic. As you play with the operational controls of a lens, the zoom, the focus, and the iris, these specs gyrate around. And a great part of the of optical design is trying to manage that movement to a degree, but you can only do it to a degree. But we will touch on some of these to give you a sense of what it is we wrestle with in a small format like 2/3 inch in high def, and then when it goes to 4 times the resolution of high definition, it's a real challenge. But from all of those parameters, 3 really emerged in the experiences with high definition television. And that was the struggle to maintain sharpness across the image plane, to maximize it to the degree possible, and then to minimize the chromatic aberrations. I'll speak about them in a moment, because they are so visible. And as the system resolution, when we went from standard definition to high definition, those image sensors could see these aberrations in the lenses much more clearly. So it put a pressure on the optical manufacturers to sort of grind them down as far as we can. As we then move forward to 4K UHD, written into those standards by the ITU, both for 4K and 8K, was high dynamic range and wide color gamut. And both of these, the lens is the first footprint on HDR and color gamut. I'll speak about that a little later. Very important. So with 4K, we have to be cognizant of these 5 key parameters. Now, to talk a little bit about the challenge, I'll just discuss a moment the relationship between the digital sampling. The camera manufacturer is the great dictator. They decide on an image format size. They decide on an image sensor with a certain number of photosites in it to define standard definition or high definition or 4K. And then they look to us optical manufacturers and to say, we need a lens from you that can project onto my sensor and fulfill its capabilities in terms of spatial resolution and things like high dynamic range and color gamut. So let's look briefly. Here's an HD image sensor, the famous 1920 by 1080. And here is the lens. That's a 2/3 inch lens. And notice the dimensions of the 2/3 inch lens there. Now, in the lens side, we don't like to talk about TV lines per picture height. We leave that to the television engineers. We talk about line pairs per millimeter. And it's really very simple. You can do it horizontally or vertically, but 1080 lines vertically is 540 line pairs. You divide that by the height, which is 5.4 millimeters, and happily it comes out at a lovely round 100 line pairs per millimeter. And that defines the band edge of HDTV, and what we call the Nyquist limit. Now, I have drawn here 100 line pairs. Don't have time to count them, but there's 100 line pairs there. And when you think that you have to squeak that through every millimeter horizontally and vertically of that little 2/3 inch lens, it gives you a sense of the challenge. And you've got to get it through with as high a contrast as possible, because that's your perception of sharpness, is the degree of contrast that we can get through the lens. And when we talk about MTF, modulation transfer function, we're talking about the modulation of the transfer of contrast through the lens. That's what MTF is all about. Now, a rule of thumb that emerged from just decades of experience is a good lens, a really good lens, will have about 80% contrast at half the Nyquist frequency. So in the case of the 2/3 inch high def, it would be at 50 line pairs per millimeter. Now here I'm showing a good contemporary 2/3 inch lens, high definition, at picture center. and you will see that the contrast is falling off linearly, which it does in most lenses. When you move away from picture center, it's anything but linear, and that's a whole other battle. We'll talk about that in a moment. But you can see that today, a good HD lens will give you about 70% at picture center contrast of the 100 line pairs per millimeter. And you can see that the half Nyquist is nicely above 80 line pairs, or 80%, sorry. Now, let's have the same discussion for a 2/3 inch 4K. Twice the number of horizontal and vertical samples. It's now 1080 line pairs. And on a 2/3 inch, that says you got to have 200 line pairs per millimeter to squeak through that lens inside every millimeter. Now here I'm showing a contemporary 2/3 inch 4K lens, and here we're achieving about 55% at the band edge of 200 line pairs per millimeter. We're just a little shy of the 80% at half Nyquist, but that's not gonna, you wouldn't notice that visually. It's in the ballpark. Now, all of us manufacturers, optical manufacturers, we usually have at least 2 grades of lenses, both in our HD lineup and now our 4K lineup. And these are reflective of a cost performance. You pay more, you get a better lens. It's as simple as that. And we have a premium lens that is reflected here, where we eke out a little more at the band edge, and we nicely meet the 80%. And that is a very sharp lens. Notice, by the way, that those lenses do go out to 8K. At the picture center, these lenses are seeing 8K with low contrast, but it is resolving 8K. You have to do that if you want a decent 4K, and HD is not that important. Now, what is it that limits MTF? Well, a German engineer back in the early 1800s, who was an optical specialist, said that a single piece of glass, you're going to be hit with 4 defocusing distortions. And they're shown there pictorially in the green. And they affect every single wavelength of light that passes through that lens. So we call them the monochromatic aberrations. And you can read there's spherical and there's coma and there's astigmatism. And then there's one other aberration, and that's geometric distortion, pincushion and barrel. Every piece of glass, now consider that a studio lens today or a field lens today can have more than 30 elements in it. And every one of those 30 elements is bedeviled with those parameters, with those aberrations there. And the whole science of optical design is to manage those rays going through one element and then using another element that might be a different glass material, a different shape, a different size, different groupings, to beat back those distortions. It's simply described like that. It's a battle against aberrations. Because if you don't, then the defocusing accumulates and you end up with a very unsharp lens. As if that's not enough, we have the chromatic aberrations. And here, as the white light passes through a single glass element, each wavelength will come out with a different focal point. Each wavelength will come out with a different magnification. That's called lateral chromatic aberration. The defocusing problem is called longitudinal. And the lateral is basically a misregistration because now the red, green, and blue are separated in size. And the defocusing problem gives you color fringing. Now, if you had a lens that did not have those 4 monochromatic distortions, nor the 2 chromatic distortions, you had a perfect aberration-free lens, you are still hit. Optics is tough. You are hit with diffraction. And that is, as you stop down the aperture, the MTF at the picture center will march down according to those curves there. And that applies to all lenses. Doesn't matter who the manufacturer is. For a given image format size, we are nailed with these curves. Now, again, it has been established over decades with standard definition and then high definition that you can live, you have to live If you play with the aperture, you cannot escape this lowering of the MTF. But it's been found that as long as it doesn't drop below 50%, the viewer generally won't see alterations visually see it, at least not very much. They are there, there's no escaping them, but that is the criteria. So now I summarize this by saying here are the boundaries to our lens MTF. The black curve on the right is diffraction. That's the drop as you stop down the aperture. Nothing you can do about that for a given image format size. That black curve there applies to Fujinon, to Canon, and anybody else who's making 2/3 inch lenses. You can't escape it. The red curve on the left, however, is in the hands of our optical designers. Enough science and enough money and enough elements, they can fight the aberrations. That curve there is the summation of the aberrations. We call it the focus limitation. We can move that to the left if we pour enough science and money into a given lens design. And that, of course, is where the real competition comes between lens manufacturers. So this is, and you can see that blue arrow there, that is your sweet range where the lens is giving you the 100 line per with high contrast. And in fact, it gives it more than that over that range. But after that, it'll start to lower both as you go wide open because of the aberrations and as you close down the aperture because of diffraction. Now, when you come to 4K in 2/3 inch and that 50% MTF criteria, now you're nailed to f8. You really can't close down more than f8 or you'll see it. I should have said it's f16 for an HD lens. You can see that there. Now that limit of f8 has been noticed and caused a little consternation over the last 3 or 4 years when 2/3 inch 4K lenses and cameras went out there worldwide and doing a lot of sports especially. The lens operators did notice it. However, they do learn to combat it. These limitations, these operational limitations. Happily, lenses or cameras are a lot more sensitive today. So with higher sensitivity, with shuttering, with ND filters, you have a lot of other variables you can play with that help you manage this limitation. But it is a fact of life. And for the 4K lens, that blue arrow giving you the sweet range, you can see is much more restricted. The sweet range in there is like from that particular lens about f1.7 to f4. Now, I've talked about the lens so far, but we do hang the lens on a camera. So let's take a look at our 4K lens picture center. I said maybe 55% at the band edge. Now we put in the camera MTF, and that's this curve there. And you will notice that it is falling off far more rapidly than the lens. It always has in every camera. And it ideally should drop to 0 at that Nyquist point. Because if it crosses to the right, that's when you generate aliasing. You get this interference pattern that bounces back into the in-band portion. Now, over the years, the lens camera manufacturers have become very practical. They all generally push that curve to the right, knowing that they can live with a certain degree of aliasing that they would see with test charts, but generally will not see with live real-time pictures from the real world. Now, what is delivered by the camera is the multiplication, the convolution of the lens MTF and the camera MTF, and that's that shaded curve there. Now, we shade that because over the years, it was learned, over many years, that your perception of sharpness from a normal viewing distance, not with your nose up against the screen, but from your normal 10, 12 feet from a 60-inch screen, is related to that area. And a guy called Hennecker in Europe says it's directly related to it. That was back in 1980s. But long before that, a gentleman called Otto Schade at my beloved RCA research labs did an extensive work on photographic and television systems and established that our perception of sharpness is proportional to the square of the MTF area. In other words, below that yellow curve there. Now, what that tells you is that your perception of sharpness is most influenced by the spatial detail below the 1080. This is 4K, a half Nyquist. And for HD, it would be at 540. And that area above is what brings in the textural detail, which is very important. But when you have, large transitions in your scenes, mostly influenced by that lower part. Now, so far, I've talked about center of the lens, but we have to look at the fact that we have an image plane. And the lens manufacturers, we all have our zones in which we determine our designs. This is the Canon Zones. Other manufacturers have variants on this, but our central zone, the most important zone, is a circle whose diameter is the picture height. Then you have that middle zone, an outer zone, and then you have the four corners, the extremities. Now, you can obviously see the reason for that important part there. When you have a close-up, you would not want to see any diminution of sharpness within that circle, or you would notice it in that central zone where the central action is. And you go even closer, it becomes very important. So the name of the game in optical design is to take that MTF curve, which is falling off from picture center, keep it as flat as you can in that central zone, and then to the degree that you can, keep it up in the middle and outer zones. And that's where the real battle of optical design is all about. You have these spherical elements, and the rays are coming in at different angles. And the best, of course, is when it comes in at right angles. But when you have extreme wide angle rays coming in, you would need a very large sphere if you were to make it hit at right angles. So we have to make compromises in the shapes of our lens elements. When we went to UHD, still inside the 2/3 inch format, the battle was to try and get that central part up and the outer parts up. And then that premium lens, we nudge it up a little bit more. Now, the importance of these outer zones is obviously the central action there is where most of us are focused. But, if you look at the top left, Konica Minolta, who have paid for that ad, would not be too happy if that was blurred because of a lens that's not doing justice out there. So these are the reasons we pay a lot of attention. And you can have events where the central characters may not be in that sweet circle in the middle. And you certainly do not want to see them looking a little fuzzy. Then when you do bring in wide angle scenes with lots of detail in them in the corners, you would rather not see a sharp drop in sharpness. When it's gradual, generally the viewer doesn't notice it too much. All right, so that's it on sharpness in lenses. Now, I mentioned earlier the new considerations of HDR, which were born in the work on 4K and 8K, but in the publications on HDR specifications from the ITU a few years ago, they squarely brought 1080p in as a UHD format. They say 1080p with HDR and with wide color gamut is a valid UHD format. And that very famous football match of 2 months ago, that was shot entirely in 1080p with Fox Sports, was upscaled to 4K for streaming services. But it went out at large with as 1080p. So HDR in the HD word is extremely important. And in fact, there's a school of thought among most of the United States broadcasters that 1080p with HDR, wide color gamut, is a sensible transition step before downstream considerations of 4K. So let me explain HDR and the lens. I'm showing here a scene on the left, the brightness, the luminance coming from the scene. into the lens projecting onto the camera image sensor. The vertical axis here is dynamic range. The camera manufacturer is the first determinant. They know their image sensor. They know its dynamic range, and then they decide, where will I put reference white? The gain calibration from master gain at 0 dB. They make that establishment. And then that defines what they have for handling overexposed signals. The lens, I will discuss 3 areas in the lens that we have to be very attentive to. But let me start by saying the lens and the camera both have a problem at the lower end. The camera has a noise floor, and the lens has an optical noise floor. You don't normally hear that term, but let me just say that it is a number of difficulties we have that contaminate the black. And you would really like that to be below the noise floor of the camera. Now that tonal reproduction, that nominal exposure, is what you set up when you use the famous grayscale chart. And you set your black levels, you set your white exposure and gammas and all that. And that is your sweet part of any picture capture. You want most of your central information to be within that dynamic range there. And then outside of that, the speculars and any overexposed signals that add that extra degree of image enhancement is the overexposed signals. But I do want to stress that HDR goes both directions. Yes, the speculars are very important, but equally important is how deep down into shadows can you go with that lens camera combination. And the lens is the first footprint on that. Very, very important, especially in maybe not so much in sports, but in drama, in movie making, etc. An awful lot of scenes are deep shadowed scenes, candlelit scenes, with a lot of detail in those deep shadows, and they want to extract that. Now, here's the challenge. A lens, any lens that has a bunch of elements in series like that, without coatings, you lose 4% by reflection at each lens air surface. So it only takes 8 lens elements and you've lost 50% of the light through the lens. The reflections that I'm showing there, they scatter, and that's what causes the splashing around of the blacks. They contaminate the blacks. So coatings were invented back in World War II in binoculars, we believe, to combat this. And the coatings is a very deep science where you deposit a quarter of a wavelength of a material on that glass surface, which generates a secondary reflection which cancels those reflections. You try to make that as perfect as possible, and that depends on your deposition accuracy. Also, the material that you use will only handle a range of wavelengths. So you have to put in multi-elements, different elements on each element, glass element, surfaces of depositions of these coatings to straddle the 400 to 700 nanometers. So this is a huge part of the science. Lenses are noted for their ghosting and flares, and this has to be battled also, especially in HDR. You would not want contaminations like this. And you see today all sorts of, as well as the multi-layer that I'm showing there, that funny looking thing on top where all the holes in it is something new we brought out 2 years ago in our second generation 4K lens, air sphere coating, which was, if you will, the final blow in nailing ghosting. And that's been very successful. It's not just optics, it's the optomechanical strategies. The lens elements have to be held very firmly to withstand temperature changes, etc. And light can scatter underneath them and cause these reflections. So there's a lot of strategies in frosted black paints, hair flocking, anti-reflection grooves. Everybody has their own secret sauce for combating this. And that's a big, big, important part of HDR. So once we deal with the noise floor the best we can, we then have to look at what does the lens do with scene speculars? And I give you an indoor scene and an outdoor scene there. And what you would like to do in that indoor scene is expose the lens camera so that you can see the details of the logs in that dark fireplace, while at the same time not messing up the reproduction of those colored speculars on the Christmas tree and those lights on the mantelpiece. In an outdoor scene, the speculars on the water and those behind the clouds there, you would like to reproduce them as accurately as possible. But again, HDR, the deep shadowed areas, you would like to be able to see the color of the clothing of the lady sitting on that dark boat there. And that's what HDR is all about. And then last but not least is what will the lens do when you get a very strong highlight, like the sun comes in at an angle that you really wish it didn't, or car headlights at night. And some tests that were done just to give you a sense of what can happen. This was done on cinema lenses in London last year. We were part of this with a whole bunch of optical manufacturers, and they were throwing the book at us. We had the model there, and then they just blasted it in a studio light. And you can see what's happening here. We have what we call a veiling glare, washes across her and just knocks the contrast. Or you can have artifacts like that. And then you can have a lens that's doing a reasonably good job like that, and it goes on. But this just gives you a sense of the three battles we have in lens. All right, I'll now tell a tale. I promised 3 tales. I tell a tale of the latest in an ultra telephoto lens, just to give you a sense of what it takes to make a second generation 4K 2/3 inch lens. These were some of the comments we got with our first generation about 4 years ago. People did see fall off on large displays, 60, 70 inch displays. They did notice that 4K made HDR and wide color gamut made chromatic aberrations more visible. So we had to grind those down even more. And then the production people, they were saying, hey, we got 4K, we got these huge displays, we got to have more framing options. We got to capitalize on what 4K is promising. And then image stabilization. The vulnerability of a 4K lens camera system to the smallest perturbation that will instantly detune that 4K sharpness. So the framing was the big one. They wanted more focal range, and at the same time, they wanted more angles of view. And the reason is sports is expanding worldwide to all sorts of things that go way beyond the football field. And of course, there's the famous venues where you're on mountains, trying to capture folks who are a long distance away. So criteria that we set was to say, all right, let's take a subject who's 6 foot high, put a little margin above and below, and we want to fully frame that subject from 1/4 mile away onto a 2/3 inch sensor, fully frame onto that sensor, 5.4 millimeters high. And there's a little formula at the bottom that tells you what the focal length must be to do that. The height of the Y is the height of the subject, H is the height of the sensor, and L is the distance. So you plug in the numbers and it says if you want to put that person there, fully frame on that little image sensor, you need 1,000 millimeters. And also they said we want a wide angle of 60 degrees so we can capture stadiums like this. And we ended up producing 2 lenses. To do that, the 1,000 millimeters and the 60 degrees took 122:1 zoom. Then we made a baby brother. Not everybody wants that wide range, but we made a secondary. These are the 2 lenses we introduced about 1.5 years ago. Now let me demonstrate to you what a focal length of 1,000 millimeters and then a wide angle of 8.2. I'm going to activate this and we're going to zoom. Both lenses, that's an HD lens below, 95 by, and then the 122 by on the top. They are fully zoomed in on a subject that's very far away, and you can see the 1,000 millimeters gives you a much bigger framing of that distant subject. So now let's do the zoom. I'll activate the zoom. You can see that that little guy is a long, long way away. And by the way, and you see the wide angle on the top compared to the bottom, the difference between 8.2 and 8.6 millimeters. There are directors and camera operators who will kill for that. But to have 122 to 1 zoom could only be done with a small format, as you will see later when I discuss the larger formats. It's quite extraordinary where we've evolved today. All right, so next, image stabilization. I mentioned that when you have a large lens and camera that could be 100 pounds and more, and it's 4K, and the guy has got razor sharp focus, it only takes a slight movement of the wind or a vibration of a tower that they might be on, and you will damage that 4K sharpness. So for that reason, we had to go in and tackle image stabilization. Image stabilization in lenses is basically you have sensors that sense the movement, the vibration, the perturbation, then report that into a high-speed processing system, which actuates a lens showing near the rear there, horizontally and vertically to counteract that vibration. And I'll just show you quickly that it's a high-speed digital system. These have got better and better over the years, but we had to go all out when it came to 4K in a small format. And so now let me give you a demonstration of that lens I just discussed to show you what we've been able to achieve. We have the lens mounted on a camera. It's at full telephoto. That little simple chart there is a long, long way away. The lens and the camera are mounted on a jig that's going to vibrate the lens and camera 15 hertz vertically. 10 to 20 hertz is the range where tower vibrations and wind will get. So that 15 hertz is an important. So now watch. We'll go to, here we are, we're vibrating 15 hertz vertically, and in a moment, there you go. And you will see there's no blur on the writing. You will see a minuscule movement of it if you watch it closely. The whole image is sort of moving, gyrating a little bit, and that's simply because we just can't do 100% reduction of that vibration. But that's a very severe test. And there's been a very positive reaction to this. And now I'll introduce Aria. I'll tell you another story, another tale. Aria is probably conjures up pictures of a duet singing an aria. Well, this duet is Sony and Canon. 2 years ago, our engineers got together and said, you know, there's been a problem in long zoom lenses forever. That is illumination attenuation. I'll explain that in a minute. So ARIA stands for Automatic Restoration of Illumination Attenuation. Bit of a mouthful. What we do is our lens, I told you there's an electronic communication on that standardized mount between the lens and camera. And we're sending in digital data reporting in real time the movement of the zoom. Sony takes that and they have a gain control that they digitally control in synchronism with the movement of the lens. When the lens zooms out, it hits a focal point, after which it ramps. In other words, the light drops. And this has vexed camera operators and directors for the last 40, 50 years. But this works incredibly well. There's been a tremendous reception to this. And indeed, we're now expanding this to our competitors are now going to join in, even though Sony and Canon developed it, that is going to be spread among our optical competitors. The other one is more difficult. Peripheral illumination, all lenses roll off the light from the center to the extremities, and that's variable. This is why we used to have shading correction in lenses with parabolas and saw teeth and all sorts of analog things, try and flatten that. Well, here we have, and you can see the variant of the curves, the roll-off, with aperture and with zoom. The three pictures are different telephoto settings. So it's a variable, it's dynamic as you play with the zoom and the aperture. So this time, the lens is sending in information on zoom, focus, and iris. And here Sony does dynamic gain control across the image plane. As the lens is dynamically in real time, moving these variables, they are controlling the gain to flatten that video across the image plane. Works superbly. All right, I've exhausted you on 2/3 inch. Now let's jump up to the two larger formats. And I call it a tale of two formats from here on out. And to remind you, it's the Super 35 and the full frame. Now, Super 35 was born in the motion picture film world decades and decades ago, and SMPTE standardized various formats. The one at the bottom was the one that was selected by the first camera manufacturers around 2005, when the first Super 35 digital cinematography cameras appeared. They said that's a nice size for our image sensors. And at that same time, the Digital Cinema Initiative, the Hollywood studios, and later SMPTE did the standardization of the 4K DCI and the 4K UHD. The UHD, as you can see, is a crop on the DCI. Same thing with 2K and HD, 1920 by 1080. So these were all standardized. Now the Super 35 millimeter format, this is our sensor. It does vary between manufacturers. And again, it's the choice of, we each individually make a decision on the size of the photo site. And then when you have 496 photo sites horizontally, that determines your dimensions. So for DCI, we're 26, a little wider than that film format. Vertically, we're almost the same as the film format. For UHD, we come in a little bit, 24.6 millimeters, very close to that film. And this is just to give you a quick sense of how different the cinema world is. These lenses that we have for Super 35 and full frame, we have prime lenses. We have various types of zoom lenses. At the bottom are our top end, the high-end cinematography lenses. Then we have the compact zooms, and then we have the ones for the television side of the world, the cine servos, with the familiar servo drives that we're used to in the broadcast. Then we have mini or compact cine servos and primes. So just to give you a sense of the challenge, I'm going to do the same calculation we did earlier for the 2/3 inch. And here we're looking at 4K, and we're looking at Super 35. And you can see when you make the calculation now for 4K, you come in at 78.2. We call that 80 line pairs per millimeter, as compared to the 200 line pairs per millimeter for the unfortunate 2/3 inch lens. So it does tell us that these large formats are more forgiving in terms of the demand on resolution, which of course does allow us, we do have the science to exploit that, and we can have much sharper imagery with these larger lenses than we do with 2/3 inch. And of course, that's very, very important for movie making and for episodic television. So just to give you a sense of some challenges, I'll tell you another tale of a recent ultra telephoto Super 35 lens. A very vexing thing was discovered as the television world started to move documentaries and wildlife from the 2/3 inch and started to, because they love the cinematic look, they said, all right, let's grab some of these zoom lenses. And this is one showing our lens on the Aria camera. And that lens there at the time was our longest zoom. It was a 10:1 zoom. Now remember, I just described 122:1 zoom. And these wildlife people found 10:1 doesn't come close to cutting it. So they exploited 2/3 inch long zoom lenses. We can get 40:1 in a portable lens in 2/3 inch. And with an adapter that blows that up to Super 35, of course, you take a hit of 2.5 stops. And when you hit twilight, again, it fails. So there was a plea. What can you do about, for the first time, give us a decent zoom lens in Super 35? And the request that came was, what we want to do is frame, we're mostly shooting animals, we want to frame a 4, 5, foot high subject from a distance of 100 meters, fully frame them. And if you can give us an extender, which has never been done before in a Super 35 lens, that would be a benefit. But this was the killer. They said, we got to hump this equipment through the jungles. So we know how big these zoom lenses get. You've got to keep this within 15 pounds and 16 inches in length. And that was a tremendous imposition on us. And here's why. I'm showing you here four, I'm not identifying the manufacturers, but these are four well-established, well-loved Super 35 millimeter long zoom. They're called long zoom in the cinema world. But you can see the zooms, the longest one, 12 times. And it's been that for 25 years. But look at the weight at the bottom of these lenses and look at the length of them. And keep those numbers in mind. So what we said is, all right, we will frame that 4 to 5 foot high subject, and from a distance of 100 meters, make the calculation that says we need 1,000 millimeters. And the final design was this Super 35 lens here with a range extender. It goes from 50 to 1,000 millimeters. That's 20 to 1 zoom. And that was pushing it. Now, obviously, these folks would have liked a 40 to 1 zoom, but they said no more than 15 pounds. And we brought that in at 14.5 pounds. Remember, a 12 by weighs 27 pounds. So this was quite a miracle. Our optical designers told us that this was the greatest design challenge they ever faced in broadcast or in cinema, to achieve that size and weight with a 20 to 1 zoom, 4K Super 35. And it called for radical redesign of the opticals and totally new design of optomechanics. And the inside is more simple, less elements than you would see in a field lens like that 122 by I showed you earlier. And it has new glass materials and a lot of aspherical designs used and a totally new layout. It took a lot of strategies to come together. And at NAB, we had planned to introduce that little lens below that big guy that I just described. And this lens down here is a lens that we believe is one that has been asked for by an awful lot in the industry, television and movie. 25 to 250 is a very sweet range. And again, look at the weight that we managed to achieve, 6.7 pounds, as compared to some of those that are 10 to 18, 20 pounds. All right, that's Super 35. Now I'll talk about full frame. And full frame, as you know, is what's central to the still photography world. And that is the famous 36 by 24 millimeters. Those of you who shot slides many years ago, that was the dimensions of your slides. And it has a 1.5 to 1 aspect ratio. Not quite a television aspect ratio, but that's what they use. And today we're living in a world of DSLRs and mirrorless, both of them using this full frame. And 4 years ago, Sony pioneered the movement into full frame digital cinematography with their Venice camera. And that came out adhering to those dimensions that I just showed you. Since then, there have been variants on that full frame, and we are one of them. I'm only showing 3 here because it would get too busy. There's about 5 major camera manufacturers now with full frame. And each of us have our variation on a theme for different reasons. I'll explain ours. What we said was, all right, we accept that full frame, the diameter of it, what we call the image circle, 43.2 millimeters. We will make our sensor, we don't like 1.5 to 1 because we're dealing with motion imaging. We make the sensor shape it to 17 by 9, which is the DCI cinema aspect ratio. That way, all of our photo sites will be deployed. There'll be no cropping. Now, when we make the calculations, that sensor is almost 6K. It's larger, therefore we can put more photo sites in. We go to 5.95, 5952 horizontal and 3140 vertically. And when we make that calculation on the line pairs per millimeter, guess what? It comes out around our friendly 80 line pairs per millimeter that we have in the Super 35. Now, what are the advantages of large format sensors? This is a big discussion in the industry today. And if you go on any of the websites of the cinema folks, you'll find a lot of still ongoing discussion. So I'll just summarize it. I'll summarize it by saying it's all about giving a few more creative tools to the DPs and the directors as they consider different types of programs, be it a major movie or episodic television, document, or whatever. But let's first of all talk about the impact on angle of view. If I put two cameras side by side, one being Super 35 and one the larger full frame, and they are the same distance from the subject, and we adjust their focal lengths to be identical, under those conditions, the full frame camera, lens camera, will capture more image, more of the scene. And this is the relative capture difference. These two rectangles, I calculated their areas on the left and I divided the 4K into the 6K. And you see that it has 2.1 times more area. So let me show you that with simulation. Here's a wide angle scene. And now I'm going to shoot that scene with these two cameras, the 4K in the center and the full frame higher resolution on the outside. So the 4K would capture that and the full frame would capture that. Notice that the full frame is capturing the mountains in the background and the bridge in the foreground that the 4K is not. And that the 5.9K is capturing the cathedral on the right and many boats on the left that the 4K is not. Now, this is when both cameras have been set to identical focal lengths. This is important. But the important point is you are getting more image content at the same resolution per unit area. This is so important. So when the movie maker wants a panoramic shot with extremely high resolution, they will favor the full frame because they can exploit that to get more image. Now you can do a small conversion on that and say, all right, let's look at image sharpness. If I shoot this scene, the one I showed you a moment ago with the Super 35, and it's 4K, and now I say to the 5.9K full frame, frame that same image. Adjust your focal length to give me exactly that image. Same image content, but now I'm capturing that at almost 6K. When I downsample that in the camera or in post-production, I will get a sharper 4K than the native 4K camera. That can be important for certain productions. So you can play that issue of image content and image sharpness. The other thing that the large format brings, the full frame brings, is flexibility in a single camera. You could put the full frame lens on prime or zoom and capture that full 5.9K, or you could mount a Super 35 prime or zoom, and it would project a smaller image. And in the menu of the camera, you say, give me a 4K DCI or 4K UHD extraction from that. Or you can put in a Super 16 millimeter lens and say the same thing, give me a 2K DCI or an HD 1920 by 1080. Or even a 2/3 inch broadcast lens with a little adapter that blows up the 2/3 inch to 16 Super 16 size. You lose one f-stop in sensitivity by doing that. But again, you get a 1920 by 1080 or a 2K. So that ability to have one camera and flexibility in lens mounts for different types of production, very attractive to rental houses and some production folks. Now, famous subject, depth of field. The impact on depth of field. If I put my two cameras side by side, same distance from the subject, Super 35 camera and then the larger full frame lens camera, and this time I say, adjust your focal lengths, your respective focal lengths to capture the same picture content, something like I showed you a moment ago. Under those conditions, when they are equal picture content, the Super 35 will have a shorter focal length. And it's that shorter focal length that gives the deeper depth of field to the Super 35. If I replace that Super 35 with a 2/3 inch and frame the same picture, the focal length would be much shorter and much deeper depth of field. But just looking at the full frame of the Super 35, this was a shot we did in our lab. On the left is our full frame camera, on the right is a Super 35 camera, and we've adjusted the focal lengths to give the same framing. And you will see that the one on the left, the defocusing of points of light behind the lady, which by the way are very close to the lady, is more defocused than the one on the right. So it's a shallower depth of field with the full frame. And it's because it's got the indirect effect, got the longer focal length. And that's what gives you the shallower depth of field. This was a demo we did at IBC a year or two ago. This was the Super 35 lens camera. And notice the background. And now here's the full frame. And you'll see that much shallower depth of field. Go back again. And that depth of field is a creative tool, very much used in movie making. If I want to focus your attention on the twinkling fingers of that instrument player, I can defocus the foreground and the background. And I can do all sorts of tricks with things, give you that table in the center and defocus the foreground and background. And then the creative folks will play with that. They will rack focus between one table and another, between one speaker and another. You see it all the time in episodic television and movie making. That's why depth of field is so sacred. All right, let's jump now from the lenses to the image sensors and associated processing, just to give you a sense of contemporary digital cinematography cameras. I'm going to use two cameras that we've just recently introduced, the famous C500 Mark II and the C300 Mark III. They are physically identical. What distinguishes them, makes them two separate cameras, is the imaging section. One of them is full frame and the other one is Super 35. And the Super 35 directly generates 4K or 2K RAW or 4K DCI or UHD, and that's captured as XF-AVC, which is based on H.264. Now, the single sensor is just that. It's a single sensor that encoded with this, it's a black and white sensor, but on top of it is put these colored filters. And that pattern there is the famous bear pattern. There are twice as many green as there are red and blue. And that's because your ultimate luminance that you want to extract in the camera is more heavily influenced by the resolution of green than red and blue. Now, typically, these single sensor cameras, you come out with one wire that's carrying encoded data. And then that has to be debared. And that's an algorithmic separation of the red, green, and the blue, and a rebuilding of them into separate RGB images. That's done in most of the cameras. A variant on that is what we do in all of our cinematography cameras. CMOS sensors do allow you to get in at individual pixels. So what we do is we read out at high speed directly out of the image sensor. We read out the four components. We're able to separate them in the image sensor and bring them out in parallel. And now what we do is we add the two greens. We then interpolate the three up to 4K or 4K green and 4K blue. We then do some processing and then downsampling and filtering to get the 2Ks. And that makes you spectacular 2K or HD, 1080p. On the left at the bottom, we separately bring out the 4 components as our raw signal, and that's a whole separate processing, how we deal with raw. But to get the normal recording of RGB, we then matrix them to YCBCR. But this is a great way of getting very high quality 1080p HDR wide color gamut. The way it works, at the top I'm showing native 2K. If you're originating 2K or HD, you have the yellow is your wanted information, your MTF of the baseband signal, and then that sideband is what causes the aliasing. And if they cross over, like I'm showing there, you will get aliasing. The only way you can do that is to filter more and pull that green, yellow to the left, the sideband to the right, when now you lose MTF. By oversampling at 4K, you can see I can live with that crossover in the 4K, and it has a bigger belly over the 2K passband. And if I do some good downsampling and filtering, I will get extra MTF shown with that green shaded area and much better separation of the sideband from that baseband and get a superior HD or 2K. In the large format, the same thing, that 5.9K, we read that out. Again, the components would be higher resolution than I showed you for the 4K, but we do similar processing at the 5.9K. We call this oversampling 5.9K processing to make superior 4K. And that's how we get 4K with higher resolution. And these are very important. Folks who want to do very high-end movies or episodic television do like to have the masters with as high an MTF and minimum aliasing as possible. So that's just to give you a snapshot. Each of the camera manufacturers have their own tricks and sciences, and they're all quite remarkable. Another variation on a theme, large format, full frame for an HD camera. Forget 4K, forget 5.9K. If I take that large sensor and then just take an HD center out of it, I end up with a very large photo site. And I'm showing it drawn to scale there. That green is the photo site of this HD compared to the photo site of the Super 35 I showed you a few moments ago. Much, much more area. That area is sensitivity and dynamic range. But sensitivity is what we saw it here. Now, there's a problem when you have a large photo site. People don't know this, but it takes time to get electrons out. There's a whole semiconductor formula for that. So we have to do some very innovative things with shapes of the various layers, etc., to speed up the transfer. But that was part of the process. And then this just describes how complicated it is to get those electrons out. Very, very high science here. But this is a camera that's an HD TV camera with a speed of 4 million to 1 ISO. 4 million to 1. And these are pictures that were made in the dark of night. It makes color pictures at night. Now, obviously, there are lights on the ships and there's some small lights there, but there are no illumination per se. And you may have seen in July 2018, I think it was, Earth Live by National Geographic did a 5-continent live broadcast of animals at night, nocturnal animals, and used this camera quite a bit. And it can be used down in the deep, dark ocean and on all sorts of wildlife and documentary and even night skies like that. So large format can give all sorts of benefits to all sorts of and then I'm going to wind up with just a final tale, and that is a new era has arrived, and you will see it with our company and you will see it with some of our competitive companies, those who make cinema cameras and still photography cameras. there's a blurring taking place where we're endowing our still cameras with just awesome video capabilities in terms of RAW, in terms of 4K, and now with a camera that we will formally introduce in a month or two, 8K, would you believe? So as well as giving tremendous flexibilities for still photography, being able to grab frames at high resolutions, etc., this does offer the possibility of these being B and C cameras to our cinema cameras. And ourselves and some of our competitors are putting PQ and HLG into these for high dynamic range. We're putting our log curves into them so that they are a better marriage. So I just leave you with that thought, and thank you for your attention. And that's my tale of three formats.
Thank you, Larry. I appreciate your time today. And thank you, Dover, for introducing him and giving us all the information and background on Larry. Larry, again, thank you for this great presentation. It's very informative. A lot of detail went into it.
Food for thought.
Definitely. So.
All right. Well, thank you.
Yep. Okay.
Sign off.
With that being said, we're going to sign off on this presentation from the.
Thank you all. Thank you all.
No, thank you, Larry.
Very nice working.
Thank you, guys.
Take care now.
Okay. And everybody, tomorrow we'll have another presentation from Grass Valley at 1 p.m. They're at the Grass Valley Alive and Gaming and Polling. It'll be two different presentations from Grass Valley. You'll get a link through the email from Steve tonight, and it's also on the Facebook page. So again, tomorrow's presentation, Grass Valley Alive and Grass Valley Gaming and Polling. And again, thank you to Dover, and definitely thank you to Larry for the presentation. It was a great job today. So I'm signing off. Have a great afternoon. Stay safe, stay healthy, and we'll see you tomorrow.